Okay, chapter 2, we are taking a look at motion along a straight line, or it's also known as one-dimensional kinematics. Kinematics is the study of motion. So we're going to start out with the basics, actually first defining kinematics. So kinematics, study of motion, so that's where we're starting, just how do things move, how can we describe that motion, where something is, how fast it's moving, how much its speed is changing. So we're going to restrict motion in 3 ways for this chapter. One, we're only going to consider motion along a straight line. That's the one-dimensional aspect. So it can go back and forth in only one direction. That will be changed starting in chapters 3 and 4. We'll start to introduce other dimensions. More interesting, also a little more complex. So for now, we're keeping it simpler. 2, we're only going to discuss the motion itself, not the forces that cause it. So for instance, if I am throwing something, right, we're going to focus right now on just the something has been thrown and is flying through the air. We're not going to worry about the fact that my hand is flinging it. We're going to look at that instant when it leaves my hand and is just moving through the air. So that's a subtle distinction, but we will get into the forces that cause motion in chapters 5 and 6. So that's coming too. Finally, we're also going to consider the moving object to be a particle. And a particle is either a point-like object, like an electron, something that is so tiny that it's just a little dot right there, like boop, there's our particle. Or an object that moves so that each part travels in the same direction at the same rate. So there's no rotation, which is something we'll get to in later chapters as well. But there's also no stretching or weird wiggling about. We don't have to worry about any of that. We can just treat everything as moving. So it's just a single point in space, which simplifies our calculations. All right, so to describe motion, we're going to define some variables. Some of these may be pretty familiar to you already, but we want to make sure we're all on the same page with understanding them. First up, we have position. Position is measured relative to a reference point. That reference point is usually the origin, the 0 point on an axis, right? So on an axis, there's a point that's labeled 0. So we say position is measured relative to that. So you could have a position of 2 meters relative to that 0. Note that that is a positive 2 meters. Position does have a sign because you could also have a position of negative 2 meters if you were to the left of said origin. So the sign here does matter. So once we have position, we can start defining changes in position. A change in position we call a displacement. This is where things start to get more interesting because things are now no longer just a single point, but we could have 2 points and look at how those points are different, right? So we take the final position minus the initial position, and that will give us the displacement. So we can look at some examples of this, right? If a particle moves from x equals 5 to x equals 12 meters, then the displacement, or the delta x, the delta, by the way, is always going to be used to represent final minus initial. So that's a Greek letter, the little triangle, it's the delta symbol, and you can note that will be final minus initial. So final here is 12, minus initial is 5, and so the displacement then is 7 meters. In the second example, we go from 5 to 1. Now when we take the displacement, we get negative 4 meters. And the negative sign does matter because that tells us that the displacement is in the negative direction. Final one here is we have from x equals 5 meters to 200 meters to x equals 5 meters. What's our displacement? Well, our displacement only cares about the very final position and the very initial position. So our displacement is just 5 minus 5. In other words, it's 0. That's the interesting thing about displacement that's a little bit counterintuitive, is it's not about the distance traveled. You can go all the way over to 200 meters and back, and displacement doesn't care as long as you're right where you started. The displacement net is still 0. That's a good way of describing it. It's the net change in position. Right. So because we have this positive or negative displacement being possible, displacement is something known as a vector quantity. We're going to get back to this in chapter 3. But for now, all you need to know is that vector is something that has both a magnitude, a size, and a direction. So the direction of the displacement is along a single axis, because we're in one dimension here, and it's given by its sign. Either you're moving in the positive direction or you're moving in the negative direction, right? One or the other. The magnitude of the displacement is a length or a distance. In this case, it'll have units of meters or feet. Now, if we ignore the sign, the positive or negative sign that tells us about the direction, we get the magnitude of the displacement, which the magnitude here is a scalar quantity. The other way to get it is just take the absolute value. So the magnitude of our second displacement example on the previous slide of that -4 meters, the magnitude is just 4. And the magnitude doesn't have that it's moving in the negative direction. It's just saying, hey, the net displacement's 4. I don't know if it's positive or negative. So there we've defined some things. Moving right along into average velocity, it's the ratio of displacement to the time interval at which that displacement occurred, delta t. So you can write our average velocity as delta x over delta t. Once again, it's just the endpoints here that we're worried about. So our average velocity, if we want to pay attention to the units, which are really important to do, we can look at our units of displacement, and that's going to be that of distance, right? So distance is in the top with the displacement. So our SI unit for distance is meters. And then in the denominator, we have time. And our SI unit for time, as we saw in the previous chapter, is seconds. So our overall unit for velocity, average as well as instantaneous, is meters per second. Meters divided by seconds. So that's a good thing to pay attention to the units on. Now, with this definition of average velocity, let's see what it looks like in practice with a graph. So first, here's a graph of position versus time for a stationary object. So we have position on the vertical scale, right? These are different possibilities of positions that you can have in X, and then time is passing on the horizontal scale. So in this case, we have an object that starts out at X is equal to -2 meters, and after 4 seconds, it is still at that same -2 meters. It has not moved, right? Even before we started paying attention, it was at X equals -2 meters. It's a stationary object. It's pretty boring. But if we took the displacement, delta X, the change in X here would be -2 minus a minus -2. It would come out to 0. So our average velocity is 0 because it is indeed a stationary object. Let's look at something a little more interesting. If we look at a graph of position versus time for a moving object, in this case, a very cute armadillo there, we notice that time is equal to 0. It's no longer at X equals -2. It's at X equals -5 down here. And then after 3 seconds, it's covered a lot of ground. It's gone from -5 all the way up to 0. And another second later, it's gone another 2 meters to get up to +2 meters, right? So that's depicted here with a X axis to show the position of the armadillo, right? That started at -5 and it is moving to the right, continues to move to the right, continues to move to the right. In all 3 pictures, it's just moving along that number line. One dimension yet again. So this is showing that the position is changing as time passes. Now, if we want to pay attention to the average velocity, then we can get the slope of a straight line that connects the 2 endpoints, right? So depending on the time interval of interest, here they focus on 4 seconds and 1 second. These are the 2 endpoints. And we can say, hey, how much displacement passed during this time? What's the difference in X? And we have 2 minus -4, and so that comes out to a displacement of 6 meters. That would be our rise, right, over the run for calculating the slope here. The run is a difference of 3 seconds, and so we have 6 meters divided by 3 seconds for an average velocity of 2 meters per second. Right, and that's just on average over those 3 seconds, the armadillo is going about 2 meters per second. It's not going to always be exactly 2 meters per second. The armadillo even could have had wild fast streaks where it started sprinting and then stopped dead for a while and didn't do anything. It was plain dead maybe, and then started again, right? But we just know on average, it's 2 meters per second. And this one is a positive 2 meters per second, because the sign here once again does matter. If it's a positive slope, that tells you it's a positive average velocity. If it's a negative slope, if it's going downward as time passes, that means it's a negative average velocity. And it also tells you, the sign of the velocity tells you that it's moving in the negative direction. So that's what we have with our average velocity. If you're fresh on your calculus, you might have an idea of how we get our instantaneous velocity, but that is yet to come. So hold on to your thoughts there. But stay tuned, because more is coming. Before we get to that, average velocity is also similar, but not the same as average speed. Average speed is the ratio of the total distance covered to the time interval over which it happened, delta t. So this is not the displacement. It's not looking at just the endpoints, final minus initial. This is looking at all of the distance covered. So if you went from 5 to 200 back to 5, then your distance is not 0. Your distance would be 195 times 2. And the average speed is always positive because it doesn't have any direction. It's just telling you on average how fast you're going. This is closer to what a speedometer has, that say a police officer has if you're speeding down the highway, hopefully not speeding too much, right? They don't care about the direction you're going, they just care how fast you're going. So an example here, a particle moves from x equals 3 meters to negative 3 meters in 2 seconds. So if we looked at this, the displacement here would be a negative 6. Negative 3 minus 3 comes to negative 6 meters divided by 2 seconds. So the average velocity would be negative 3 meters per second, but the average speed is going to be positive that. It's just going to come out to positive 3 meters per second, because all that we care about is that the distance there is 6 meters over that 2-second interval. And so it comes to 3 meters per second. So now we've gotten an introduction to kinematics, our study of motion, and some of the variables we'll use for it: position, displacement, average velocity, and average speed. Stay tuned, there is more to come.